Chapter 7, Section 1, Day 2 is more about exploring exponential models. There are 6 of the more popular reasons we might want to use exponential functions to model real-world situations. Those things that are probably something you'll experience in your lifetime include things like interest-bearing savings accounts and depreciation value. Located on the bubble is your exponential growth and decay function. If you take a look at that, the little letter a, lowercase letter a, is the initial amount. When it comes to loans and things like that, they'll call that the principal. 1 plus r is the b value, which is your growth or decay factor. The r is your rate of growth or decay. Given to you as a percent, should be changed to a decimal to work with it. And t is the time in years. Number 1, you invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? So start by writing down the function and fill in what you know. I know that the 1,000 is my initial amount. The rate, 5%, needs to be changed to a decimal. It says how much money will be in the account after 6 years. So we're looking for a of t. You can type it into the calculator exactly the way that you see it. You should get $1,340.10. Remember to round any money values to 2 places. Example 2a. Suppose you invest $500 in a savings account that pays 3.5% annual interest. So again, I'm going to start with the formula that we're given. And fill in what we know. We know that we're investing $500. And I know that the account pays 3.5%. So that's 1 plus 0.035 inside parentheses, and we want to know how much it's going to have after 5 years. We'll put it into the calculator. We should get $593.84. Letter B, when will the account contain at least $650? This one's a little different because that $650 is your A of T amount that we're used to ending up with. You're still starting with $500 in the account, and your interest rate is still I'm actually going to change this. Instead of plus 0.035, I'm going to make that 1.035 all the way, and I'm looking for T. So think about how you learned how to solve this in Algebra 1. First thing we need to do is divide by 500 so that those cancel. On the left-hand side, 650 divided by 500 is 1.3, and on the right side we have 1.035 to the t. Now, because t, the variable, is in the air, you have to solve this considerably different than we're used to. The first thing we're going to do is consult the calculator. So in the table function, if you have something there, just clear it out. I'm going to put 1.035 to the x. Press enter. Your start should really be, at this point, higher than 5, because we knew at 5 years it was only $593. And I'm going to step by 1/12 because we can narrow this down to months. So go ahead and put that in and scroll down until you see the 1.3 we had on the left-hand side. You're looking for the y value of 1.3. And it seems to happen right there at 7.67. So that means my answer is 7.67 years. Number 3, suppose you buy a car for $18,000. The salesman said that the dealership would buy it back at a 25% depreciation. That's important, that's decay. Value at any time. How much will your car be worth after 3 years? I'm going to start with A of t again. Now I'm going to make it 1 minus r because it's decay. So my initial value is $18,000. My rate is 0.25, and I want to know what's going to happen after 3 years. Take a second and put that in your calculator. $7,593.75. Don't forget that when you're looking for the variable t in the air, you do need to use the table function. If they don't give you a rate of change, you have to do that first. I want to point out in this one that you do have to take the absolute value in the numerator. You ignore any signs that are there. But then if it is a decay or if it's depreciating, you do need to make it negative before you keep moving. So example 6. In 2009, there were 1,570 bears in a wildlife refuge. In 2010, the population had increased to approximately 1,884 bears. Now I'm going to pause there for just a second so I can find the rate of change. The rate of change is the initial, so there were 1,570 bears, minus the final, 1,884, absolute value, of course, divided by the initial, 1,570. So take a second and put that into your calculator. When you put it into the calculator, you don't have to worry about the absolute value part. Just do everything else, and then just take your answer and ignore the sign. So you should find that your rate of change is 0.2. If this trend continues and the bear population is increasing, so that means that this is actually a growth rate, not a decay. They want to know how many bears there will be in 2018. So it's like I'm starting the problem from scratch. I'm going to do a of t equals little a times 1 plus r to the t. My little a value is where we were initially. Initially, there was 1,570 bears. I'm going to add my rate in there. And because we want to know how many there will be in 2018, that's 9 years after 2009. So take a second and put that in just the way you see it. Now, you'll find that it's 8,100.86, but you can't have 0.86 with a bear, so always round down. You want to round down anytime you're dealing with tangible, real-world objects except money.